Hi, I'm Bogdanovic, SVP of Engineering at QuEra. One of the key things what we are facing today is that we are switching from prototyping into production. People are not anymore thinking about building a prototype that can execute a quantum computation. They're thinking about how to productize that. And building products, it's about creating a reliable, repeatable engineering process that will deliver the product at the predictable pace. Right now, we are receiving a lot of scientific advancements from our CTO team, but a lot of them are manual. They require a lot of manual work. And as engineering, we are trying to see how we can modularize that, make it more automated, as well as self-correcting. My background is in the telecom industry, and when I joined the telecom industry in the 90s, a lot of the things were also done manually, and with the time we automated that enabled the scale. We have the same challenges now at the quantum computing, how we can make sure that when we have a drift in the optical system, that it can be calibrated automatically using machine learning algorithms that will be much more precise than human-based calibration, to switch from a reactive to a proactive system that will be able to deliver better advancement in the science, in the scientific area, as well as in the end user, for the end users. Most of the systems that were used in the academia are mainly focused on humans, how to create human interfaces. We are, as engineers, challenged to replace those human interfaces with machine-to-machine interfaces, because this is how we can make it scalable and repeatable and automated, that the machines will be controlling each other. We have a lot of real-time challenges because, again, with the scaling, you have a very complex system, distributed system that is made out of dozens of modules that have to be highly synchronized in order to deliver the set of pulses into a fairly small atomic scale area that is creating the quantum computing artifacts. So the distributed nature of the system, as well as the real-time requirements with the scaling, are one of the biggest challenges that we have at the moment. Yes, with all this data, we are getting better insights in what state is the overall machine and which parts are out of sync with the rest of the system. Based on that, we can then very firmly decide this is the action that we have to take against that module function of the system, and we can automate that through software to execute proactively even before a human would realize there is a change happening in the system. Because one of the things what attracted me to the neutral atoms, all the qubits are the same. There are no differences. And one thing which is also very interesting, we are building for each application an ASIC in the vacuum, using the atoms, organizing them into an application-specific integrated circuit that is being done for each application. And that is a well-known process that makes sure we don't have to take into consideration many different qubit types. It is just all qubits are the same, and we just have to organize them into a very specific structure.